Hi everyone, in today's lesson we're going to talk about simulations. So let's look at the first example. In a recent survey taken, 40% of American students like M&M candy. So this 40% of American students is your population proportion. So let's write that down. Population proportion. Okay, so here's a question to think about. If you were to take a random sample of, say, 20 students at Newfield High School, how many of them would you predict like M&M candy? Well, based off of this first sentence about 40% of students liking candy, I would think that 40% of my 20 students should like M&M candies. So we would take 40% and figure out what 40% of 20. And the way we do that is change 40% to a decimal and multiply it by 20. If you do that, you should get approximately 8 students. So this population proportion helps us estimate what would happen in our samples. So let's look at a simulation that Miss Barris's class is going to do for us. Okay, each student in Miss Barris's class was given a paper bag and a bag of M&Ms containing red and blue M&Ms only. Each student was to randomly select a sample of 20 M&Ms with replacement from the bag and record their color chosen until 20 M&Ms have been selected. They then were instructed to record their sample proportion of M&Ms chosen that were red. Their percentages were recorded on the dot plot below. Red will indicate if a student likes M&Ms. So basically, a sample proportion is a percentage, so let's write this down. Sample proportion, I'll put it over here, is a percentage or equivalent decimal of red M&Ms in the bag. All right? So we're going to estimate 40%. That's what our goal is going to be. All right. Okay. The graph of all the students' sample proportions is called the sampling distribution of the sample's proportions. This sampling distribution is an approximation of the actual sampling distribution of all possible samples of size 20. So here's a dot plot of this information, and let's analyze it. So part A, what was the smallest sample proportion observed? So if you look at the dot plot, you'll see right here is about 0.15 or 15% was the smallest sample proportion. How about part B? What was the largest sample proportion? So you should see here 0.65 or about 65%. And part C is what sample proportion occurred the most. So you just want to look for the one that has the most dots. So I think this one's the winner. So about 0.35 or 35%. So what these sample proportions are observing is what percentage of those 20 M&Ms were red. So in each person's bag, it looks like one person had 15% of the M&Ms chosen be red. In this bag, 2 people found that 65% of their 20 were red. And 8 people found that 35% of their 20 were red. Okay? Okay, let's move on to part D. It says, using technology, or the calculator, find the mean and the standard deviation of the sample proportions to the nearest hundredth used to construct the sampling distribution created by the class. So basically what we're going to do is we're going to take these values down here, and they're going to go into your list 1. And then their corresponding dots, or their frequencies, are going to go in L2. So if you want to just have a quick look at what you should be putting into your list 1 and list 2, I'll give you a few of them. So 0.15, 0.20, 0.25, 0.30, 0.35. So in list 1 is what your sample proportions are going to be, and in list 2 you're going to put your frequencies. So 111, 111, then 28, 28. And you would repeat this process until you've went all the way to a sample proportion of 65. And then tell me what my mean, or my x bar, is, and my standard deviation, Sx, not sigma x. This is for a population, so you want to make sure you use SX for the sample. Hit resume once you've done so, but please pause the video and see if you can get these numbers. Okay, you should be getting 0.43 and 0.13. So let's look at part E now. It says, how does the mean of the sampling distribution compare with the population proportion of 0.40? Well, look, the mean is approximately 0.43, and this population proportion is 0.40. So they are very close to being equal. All right, because 0.43 is approximately the same thing as 0.40. Okay, let's move on to the next part. The next part says, find the margin of error. So if you recall from last lesson, you'll recall that the margin of error is 2 times the standard deviation. In this case, my standard deviation is 0.13. So I'm going to take 2 and multiply it by 0.13, and I get about 0.26. That is our margin of error that's going to help us for part G to estimate the interval for the population proportion. We know the population proportion is 0.40 or 40%. Let's see if we can get an interval that includes that. So we have a lower limit and an upper limit in this interval. The way that we find it, if you recall from last lesson, is that you're going to take the sample proportion mean and we're going to subtract the error, and we'll take the sample proportion mean and add the error. So our sample proportion mean is 0.43, so 0.43 minus the error of 0.26, and 0.43 plus the error of 0.26. When you do that, you should get an interval between 0.17 and 0.69. Why don't you take a minute, pause the video, and see if you can get those answers. Okay, so this interval tells us that the population proportion should be somewhere between 17% and 69%. And 40 definitely falls within that interval. But this is a pretty wide range. What do you think would happen to this range or interval for the population proportion if instead of sampling 20, we increased our sample? Do you think that this population proportion interval would get smaller or get bigger? Well, let's see. Okay, so that's the question that I'm asking right now. What do you think would happen to the sampling distribution if everyone in the class took a random sample of 40 M&Ms in the bag instead of 20? So, to help answer this question, the students in Miss Barris's class repeated the process, but this time they drew a random sample of 40 M&Ms instead of 20. The dot plot is shown below here. What was the smallest sample proportion observed? You should be looking here now is 0.30. What is the largest sample proportion observed? It would be here, about 0.55 or 55%. This one we could say, or 30%. What sample proportion occurred most often? It looks like there's a repeat of 2 of them. But now, what are these values? We don't necessarily know, so we can estimate. I say this is about 0.37 and 0.42. You can make up whichever one you want in between, so this is just an estimate. So I'm going to estimate to be about 0.37 or 0.42. Those occurred most often. So just like we did in the last example, take your calculator, find the mean and the standard deviation of these values here. So again, these values are going to go into your list 1. I actually don't even need these because they don't even happen. So these would go into my list 1, and the frequencies go into list 2. Hit resume once you've done that. Okay, your mean in this case should be about 0.40, and your standard deviation is about 0.05. And these values I get exactly if I use 0.37, 0.42, 0.47, 0.52, 0.32. So your numbers may vary, but that's okay. Okay, how does the mean of the sampling distribution compare with the population proportion of 0.40? Well, look at this and look at this. they're exactly the same. So they are, in fact, equal. Okay, now let's look at the margin of error. The margin of error is 2 times the standard deviation again. Standard deviation in this case is 0.05. So 2 times 0.05 is 0.10, or about 10%. So let's use this to estimate the interval. So again, you're going to take the mean proportion, sample proportion, subtract 0.10, and the mean proportion, and add 0.10. I just didn't write it all out. But this is the mean proportion, sample proportion. So 0.40 minus 0.10 and 0.40 plus 0.10. So you should get about 0.30 to 0.50. So look what's happening to the interval. It went from, on the previous page, I'll just write it down, when I took a sample size of 20, so when n was equal to 20, your population proportion was 0.17 to 0.69. So about 17% to 69%. And if I increased the population size, the 20, or sample size if you would, I went from 30% to 50%. Sorry, it looks like an X, but percent. So by increasing the n, or the sample size, I've decreased my population proportion interval. So I'm getting closer and closer to the actual population proportion. So let's analyze all this now. As the sample size increased from 20 to 40, what happened to the following values? What happened to the mean? The mean got more accurate. It went from 0.43 to 0.40. Okay, what happened to the standard deviation? Well, it actually looks like the standard deviation got smaller. So it went from, on the front page, a standard deviation of 0.13 to 0.05. It got significantly smaller. The margin of error went from 0.26 to 0.10. So the margin of error got smaller too. And what happened to the population proportion, the interval? The interval, I think, got smaller as well. It got more and more accurate. So it went from 0.17 to 0.69, so 17 to 69%, to 30% to 50%. So what conclusions can we make about all of this? Each one of these Roman numerals will correspond to those Roman numerals there. So let's read them. The mean of the sample proportions will be approximately equal to the value of the population proportion. That's true. As the sample size increased, the sampling variability, that's the same thing as saying standard deviation. So the sampling variability in the sample proportion decreased or got smaller. So in other words, the standard deviation got smaller. 3, as the sample size increased, the margin of error decreased. You got closer and closer. And a plausible population proportion is your proportion plus or minus your mean, where m is your margin of error. Okay, so tomorrow we're going to practice a bunch of this. So take a minute, jot down any questions that you might have, and ask us in class. All right, have a nice night.